online?
Let's see.
No. Okay.
Okay.
All
Just in case.
right, I would have worn a better t-shirt. All right, well, welcome everybody to this mini course. For those of you that were at my mini course in bed level last week, this course is going to be very different. Okay, what I want to do in this course is I want to examine a couple of problems. Both of these problems actually started, they were formulated and began in the 1950s. And they were both problems that were originally one-dimensional, that were set in the one-dimensional setting on the real line or on the circle. And eventually people started to think about these problems in higher dimensions. It was a natural question, but then they got stuck. The problem got stuck because when you look at the heart of the matter for these problems, it turns out there's a certain oscillatory integral. Okay, so there's some connections with this course and my course from last week. And these oscillatory integrals in higher dimensions just look monstrous. I mean, they look insurmountable, and people started to make no progress whatsoever. They stopped working on these problems. However, it turns out there's a connection with these problems and problems in Calderón-Zygmund theory. This is the point of this course. I want to explain at the heart of the matter of these problems, which are these oscillatory angles. It turns out that these oscillatory angles, this heart of the matter, is exactly the same heart of the matter for one problem and something very similar to the heart of the matter for the other problem in the problem in Calderón-Zygmund theory. In Calderón-Zygmund theory, although it's had its stops and goes, especially in the 1960s, there were some things that prevented Calderón-Zygmund theory from progressing, but because of the applications, we got through that. And Calderón-Zygmund theory, as we know, most of us here are from some of us here are from the Calderón-Zygmund school of harmonic analysis. And because of the applications, it has really flourished and it's gone beyond one dimensions into higher dimensions, into multilinear ways, into multi-parameter ways. And so now that we have this beautiful Calderón-Zygmund theory, this brings a new perspective on these old problems, and we're going to go back to these old problems and make progress again. Okay, so that's the point of this course. So let me start by convincing you that the 1950s was really a golden age in Fourier analysis. Okay, so in order for me to explain that and put it into some context, I need to go back further in time. I need to go back to the 1940s. Okay, in the 1940s, there was a very interesting conference at Princeton at the Institute of Advanced Studies. And it was a conference that looked like, so the purpose of the conference was to give a post-World War critique of mathematics at that time. So they brought together all these leading experts from all areas of mathematics, from mathematical logic to PDEs, from probability to topology, to geometry, analysis, algebra, and so on. And among the analysts representing Fourier analysis was Anthony Zygmund himself. And Zygmund gave a scathing review of the state of art, state of play of Fourier analysis at that time. Okay, so there's I put here, I finally found the conference proceedings. If anyone's interested, it's online. And there's some very interesting quotes from Zygmund himself. So I just want to read you one of them. Blah, blah, blah. So where's Zygmund? Here's one quote. The theory of trigonometric series is one of the worst places to have conjectures. History teaches that almost all conjectures were proved false. Okay. That's it. And he goes on. He complains that there is no theoretical underpinning for the subject. There's no theoretical framework in which to study general principles, and develop these principles. So he gave a rather bleak picture about Fourier analysis, harmonic analysis in the 1940s. Now come the 1950s, and everything changes dramatically in two fundamental ways. First of all, there was a convergence with a certain perspective, point of view by experts in Fourier analysis that the appropriate setting to study Fourier analysis is furnished by the setting of locally compact abelian groups. Okay, so this gave us a theoretical framework. Okay, so instead of sort of studying Fourier analysis in particular settings like periodic functions, and we develop things into Fourier series or functions on the real line, we take the Fourier transform. We could even talk about higher dimensional analogs of that. We know that we can do Fourier analysis even in finite settings on the integers, modulo, and integer. And this gives us a single framework in which to think about Fourier analysis or taking the Fourier transform of a function. So this really gave us, if you can start with a problem, even a concrete problem, and if you can formulate it in this general setting, that often allows us to see the problem much more clearly. And so this gives this field of Fourier analysis an abstraction and many other fields like topology of how to abstract things. And when we abstract things, often we see things much more clearly. Okay, so this gave us sort of a powerful, nice theoretical framework that Zygmund was complaining was lacking in the 1930s. But there was also another big, this was the decade of the advent of Calderón-Zygmund as well. With the seminal paper of Calderón-Zygmund, 1952. They introduced the real variable method. And this freed us from the complex method that was used. So the complex method is tied to one dimension. It's a powerful, powerful method. I want to study functions, periodic functions on the circle, or functions on the real line. What I do is I extend these functions as analytic functions, holomorphic functions in the upper half plane, or to functions inside the unit disk. And I use function theory as a tool to say something about these problems, and then I pass back to the boundaries. And this gave us deep results about Fourier series on the one hand, Fourier transforms on the other hand. But it doesn't really, it's not really amenable to higher dimensions of looking at multiple Fourier series or Fourier or functions on Rn. And so this started to give us a real variable method, a direct method to start to think about these problems. And so this was of course, a wonderful beginning to a theory that is still being developed. And so what I want to do is just to review a little bit. I'll start with locally compact abelian groups. I'll call G a locally compact abelian group. So that's a locally compact abelian group. So by which I mean it's a topological group. So I have an abelian group. It has a topology which is compatible with the underlying additive structure, and that the topology is a locally compact topology. Okay, so that allows us there. Of course, there are many examples. The circle group is a locally compact abelian group. The real line is a locally compact abelian group. Z to the n, the integer lattice, n-dimensional integer lattice, and we even have finite groups like the integers, modulo, and integer. Okay, so what all these things have in common is that that was not too successful. So where did we have the stick? Magical stick? Okay. Let's go there. All right. So with a locally compact abelian group, one thing we have is that we have Haar measure. Now the node M is Haar measure. So what is Haar measure on these groups? This is a translation invariant measure. I take a Borel set, I translate it by a group element, and the measure doesn't change. Okay, so this is Haar measure. In fact, it's unique up to a positive multiplicative constant. So this gives us a measure that I can start to define integrals and integral transforms, and in particular the Fourier transform. Now the other key ingredient here is the dual group, the Fourier dual group. So I start with a locally compact abelian group, and I form another locally compact abelian group. Its elements are, and I'm going to call these gamma. So you think of these as cosines and sines at different frequencies. These are mappings from the group into the circle group, which are continuous, and they preserve the additive structure. gamma of x plus y is equal to gamma of x times gamma of y. So this is in fact gives, just by the abelian structure of the circuit group, the target space, it gives me an abelian structure of this dual group. So it carries a natural abelian group structure. And the topology, there's a natural topology, which is the weak topology, so that the Fourier transform, which I'm about to define, becomes a continuous function on this space. Okay, so this becomes a locally compact abelian group. And now I can look at integrable functions on this guy, and allows me now to define a Fourier transform. Okay, so for any integrable function with respect to this R measure, I define a mapping on the dual group. I simply integrate my function f of x over the group against gamma of x, the conjugate of gamma of x, then integrate this with respect to function. This is called the Fourier transform of an integrable function. Okay, so this is and again, so the topology is defined to be the weak topology, so that these guys are all continuous functions. Okay, so we have this Fourier transform, as I want to think of it a little bit more algebraically. So as a mapping, I have the Fourier transform from L1 into, this becomes a continuous function. And in fact, we can show that it actually is a bounded function. It actually goes to 0 at infinity. And so this takes a function, an integral function, and gives me this is the Fourier transform. Okay, so this is an algebra. This is an algebra homomorphism that we'll see in a moment. Okay, because both of these are algebras. So let me just emphasize that fact. Oh, not too bad. Good. So I want to emphasize that this is a Banach algebra. Okay, so not only I can add to, it's not only a vector space, a Banach space, but there's also a multiplicative structure here. I take two functions and I can involve them and I get an integrable function. So at a point, at a group element x, I simply integrate f of x minus y, g of y, and I integrate this against okay, so that gives us a Banach, makes it into an algebra. And we have, this is actually a Banach space, it has a natural norm. The L1 norm, just to remind you, is the integral of the absolute value of f of x. And to be in this space just means that this integral is finite. Right. So now I want to continue with this. And so we have, as I can look at the image now under the Fourier transform. Okay, so the Fourier transform maps any integral function into a continuous. Doesn't give me all continuous functions that vanish at infinity. So we give us that this becomes a subalgebra of the continuous functions on the subalgebra of functions on the dual group. Okay, we call this the Fourier algebra. So we actually, and we give this, it is a Banach algebra as well. I take an element in here, by definition, it is the Fourier transform of some integral function, and the norm I put on it is just coming from the norm, the L1 norm of the function here. This gives it a Banach algebra structure, the Fourier algebra. So we have here if I want to rethink about this Fourier transform, this makes, I have this mapping, taking integral functions on my locally compact abelian group, and it gives me now a certain, by taking the Fourier transform, certain continuous functions on the dual group. Okay, so this is in fact so it is a homomorphism, just to convince you, it's easy to check that if I take a product of two elements in here, I actually get a product of two elements here, because this is an algebra continuous function, and the multiplication is just pointwise multiplication of two continuous functions. And so this is in fact how it's all set up. This is an isometric. It's just rigged up that way. Okay, it's an isometric isomorphism. Okay. So this introduces this is an important sort of aspect when you start to put things on this sort of theoretical foundation, so this more abstract formulation, you can start to ask, so we're now associating to our locally compact group various algebras. These are called group algebras. So this is a particular group algebra, this is another group algebra, in this case by the Fourier transform they're the same. They're isometrically isomorphic. Okay, so we can start to ask this very fundamental question, and I'll come back to, is that in what sense do these group algebras determine the group? Okay, if I know between two groups, G1 and G2, these are isomorphic as algebras, does that imply the underlying groups are isomorphic? It's the same type of question we ask in topology. Okay, so we have topological spaces as abstract formulation that include things like metric spaces and so on. And we have the basic morphisms in that case, which are continuous functions. And we can ask, we want to understand how to characterize all topological spaces. We want to understand how to characterize all locally compact opinion groups, okay, up to isomorphisms. And in the case of topology, it's up to homomorphisms. Okay, and what do we do in topology? Well, we associate groups, associate modules to a topological space. The homotopy group, the homology group. And so these are always invariant. If I have two topological spaces that are homomorphic, they're the same topologically, then these groups, homotopy groups, homology groups, are isomorphic. But not the other way around. Just because it's a tool to ask, if I understand the homotopy groups, to what extent do they determine the underlying topological group? We can ask the same abstract questions in this setting here. And this becomes sort of a powerful perspective that we'll return to. But okay, so that starts to lay down the sort of general formulation of things. I want to now make things very concrete. So let's go back to an old problem. This problem has its roots, well, it goes way back, like it was worked a lot in the 1940s. And what we want to understand is we want to understand mappings in the circle. Okay, so the basic question, so I want to think of this. So I take a function and then I look at this map by composing it with this map. I start with a function of the circle. This gives me another function on the circle. So you can think of this as a change of variables. So a very common problem was, I want to understand certain properties of functions of the circle, and are they preserved or not under what kind of changes of variables? It's just a basic old type of question. And so one basic old problem was to understand those mappings of the circle that preserve the space of absolutely convergent Fourier series. So absolutely convergent Fourier series, that was really something that people were really obsessed about in the 20s, 30s, and 40s. And so the question here is, this is the problem, I want to understand those mappings, those phi that have the property that is this under a change of variables, does f composed with phi have an absolutely convergent Fourier series whenever f does. Okay, so that is just a basic question. And so let's just think about this a little bit more concretely. So what does it mean? So I take a function and I develop its Fourier, I look at its associated Fourier series. Okay, so we say it has an absolute convergent Fourier series if the Fourier coefficients are summable. That all is what we mean by f having an absolute convergent Fourier series. And when this happens, then of course this thing converges for every t, converges uniformly and converges to the value of my function f. So here, the a sub n, you can actually check, are just the Fourier coefficients of my functions. I can recover them by simply integrating my function against e to the minus 2 pi I and x, respect to the eigenmeasure on the circle. Okay, so that's what we mean by an absolute convergent Fourier series. So I want to put this in this sort of general context now. So what is happening here? I want my group here is the integers. That's the basic locally compact abelian group. Okay, so the group, the topology here is the discrete topology. Our measure here is counting measure. And so we have in this case, so what is the dual? The dual is the circuit group. Okay, so let me be specific here. So if I take an element, e to the 2 pi I t, this is an element on the circle, a complex number of modulus 1, I can identify it with a real number t mod 1. So always, if I'm going to identify it with a real number t, I think about this mod 1, and here I can define a Fourier character on the integers by just taking this e to the 2 pi I t and taking in power. So as we know from basic properties of the exponential, that gives me, for every t, this gives me an additive character on the integers. E to the 2 pi I of n plus m is just the product of these two things. Okay, so this is, now let's look at what do I mean. So I'm going to now play out. What does it mean to be looking at an L1 function of this group? This is just little L1 of the integers. So of course, in L, what does it mean for a function? So this is a mapping from the integers into complex numbers. That of course just means I'm looking at a sequence of complex numbers. Okay, and what does it mean for to take the and what is the L1 norm of this guy here? Okay, so I'm integrating over the integers here. So this is the integers. I'm integrating over the integers of the absolute value of this function on the integers. I'm integrating with respect to counting measure, that's our measure, and so it's just the sum as n varies with all the integers. So I take a sequence, function of the integers, it's L1 norm, it's just the little L1, it's just the sum of the absolute values along the sequence here. And so now let me look at the Fourier transform of this function. And so what is the Fourier transform of this mapping? Again, it's just by definition, I'm integrating over the integers. I'm taking this function and integrating this against e sub t, my character, and take the conjugate and integrate this again against counting measure. So this is just the sum. So this is now a function of the dual space, which is these torus, given that I identify with real numbers mod 1. So this measure is counting measure. I'm summing a sub n here, and this is e to the minus 2 pi I n t. So the Fourier transform of a sequence is just the corresponding Fourier series. So this is a nice absolutely convergent Fourier series because these guys are summable. Right, okay, so this gives us, this is an element now. I want to think of this as an element in the Fourier algebra. This is the Fourier transform of some element, and this is an element in the Fourier algebra of the dual of the integers, which is, so this is the Fourier algebra of the circle. Okay. Right, so this is really the Fourier algebra. I want to think of this as the Fourier algebra of absolutely convergent Fourier series. Okay. Right, okay. So now we come back to this old problem. Now that I know what absolutely convergent Fourier series are, they're just the Fourier algebra of the circle group. Okay, they're just coming from the Fourier transforms of sequences that are summable. So let me now reformulate. Ooh, these are quite wet. Ouch, okay. So let me. What?
You don't want to get it back, right?
Not too wet. I have a fear of water. Okay, no, I can do that. That's all right. Sorry.
I'm gonna try to make them less wet.
Yeah. Okay, so let's go back to this old problem. I think it must be still on the board. I haven't rubbed off anything. Where is this old problem? Oh, it's right above me. Okay, so let me now think of this with this formulation. So we're just asking now which mappings, capital Phi, from the circle to the circle, okay, satisfies the following, that I have this mapping now. I take an absolute convergent Fourier series that I think of it now as the Fourier algebra of the circle. I take an absolute convergent Fourier series, I compose it with this mapping, and do I still end up in this algebra, in this Fourier algebra? So that is, are called as dagger. And so that is just a reformulation of this old problem. So that's what the problem that people were very much interested, started in the 1940s, to try to understand what are the mappings of the circle. So under changes of variables, it preserves the space of absolute convergent Fourier series. But now I want to think about the space of absolute convergent Fourier series as being, okay, so this is a subalgebra of the continuous functions of the circle. They're coming from the Fourier transform of summable sequences. Right, okay, so this is the basic question. And so let's suppose that that's our holes. So dagger. Well, let's suppose I have a mapping. Suppose that dagger. So what does that mean? That means suppose I define now a mapping. So every absolutely convergent Fourier series under this composition stays in this space. So I can define a linear mapping from this harmonic algebra of absolutely convergent Fourier series into itself. I can define this to be T of F to be the composition. Okay. Maybe put that here. Okay, so that gives me a well-defined map. And then, in fact, you can check. This is an algebra. This is an algebra homomorphism. Very simple, right? If I take, for instance, I take two functions. Remember, the multiplication here is just point-wise multiplication. So when I compose it with a map that changes sums to sums and multiples. So this is an algebra homomorphism, trivially. And so I have, whenever you have an algebra homomorphism between two Banach algebras, and the target algebra is semi-simple. Okay, so whatever that means. Okay, so that's just telling me, in fact, that all the complex homomorphisms of these are necessarily non-zero. Okay, so in that case, and this turns out to be semi-simple, so we get as a consequence, we get that automatically T is continuous, or equivalently bound because it's linear. Okay, so what does that mean? That just means I can find a constant. I can find a constant so that if I look at this composition and I take the norm in this Fourier algebra, just summing the Fourier coefficients as controlled by a constant times the norm. So we have this automatic continuity. This is kind of a big deal back in the 30s and the 40s when people were developing Banach algebras, because they made this observation. So for instance, the complex numbers is semi-simple. Okay, so any sort of bounded linear map on a Banach algebra is also multiplicative. So it's a homomorphism. It's automatically continuous. Okay, so we have these many theorems. It's a dead subject now, by the way. So, but there were many theorems that were discussing this automatic continuity phenomenon. And so anyway, this is a simple, it's just functional analysis. Okay, so now I would like to, let me pause. I'm going to pause here and rub off the board. So take a break, check your stocks, and read the paper. Let me try to, okay. All of them, yeah, let me just, I'll just take a little time. Can you drag them all down for me?
You're right, sure.
Okay. Can you pull that one down? I'll just take it in trouble. Thank you. By the way, that's a trick. It's a useful trick if you're actually giving lectures to 200, 300 students, which I had for many years, the computer science students that were at from 5 to 6 p.m. on Thursday, which is drinking night in Edinburgh, and Friday. So I fill up all the boards, and then we just take a 5-minute break. And so the noise level goes up, everyone reads the newspaper, and it really relaxes the students. So I hope you're relaxed now. So now let me find my place. Okay, so I want to rethink now this problem. Right, this old problem kind of here. Which mappings in the circle preserve the space of absolute convergent Fourier series? Little functional analysis says that this is a continuous mapping. So let's look at mappings now. I want to look at mappings. Okay, of the circle. What do they look like? Well, okay, if I take a point in the circle, e to the 2 pi I t, I get it mapped to a point on the circle, which is e to the 2 pi I of some other real number. Okay, so this induces a mapping from the reals to the reals. Okay, and because of this continuity, it's without loss of generality that I can assume that this guy is continuous. Right, and so now let's see, what does the side have to look like? Well, if I replace t plus 1, if I replace t with t plus 1, this doesn't change. And therefore, if I replace this with t plus 1, it can differ, it has to differ with psi of t by an integer. Okay, but that integer might depend on t. But because of continuity, the only continuous functions on the integers is just a constant function. So we actually have that this is identically some constant, which is an integer. So we see here very easy that this implies that psi of t has to be a periodic function. Okay, by the way, so this is plus this a linear part. So this guy is one periodic. As a function of the real line. By the way, I defined phi of t to be psi of t minus L times t. Use this property, check that it's periodic. Okay, very simple. So I have this periodic function, and then I have a linear part. So this thing, I have a periodic plus, I think of this as a linear part. This is the linear part given by the coefficient given by an integer. So that's how I think of mappings of the circle. And so let me now look at this mapping T of that. Okay. this is my composition. This is just by definition, I'm composing my absolute convergent Fourier series with this mapping. And so I have here the sum, so that's my function f here. So here f of t is my absolutely convergent Fourier series, e to the 2 pi I n t, and I'm summing over all the integers. This is a summable sequence. And now I take this change of variables and I get e to the 2 pi I n times psi of t. Where psi now has this periodic part and this linear part. Okay. Now, very easy to see once I have this. So let me call this, so dagger here. So this is, oops, seemed to be a little bit, okay. I don't know why I called this dagger, but okay. So we see, yeah, that was a little bit more. So we see that this whole problem is equivalent to uniformly bounding e to the 2 pi I n times psi. I take the norm as a function, as an absolutely convergent Fourier series, and I want to soup an n, and I want this to be finite. Okay, very easy. Suppose this was the case. I want to see that star holds. I want to see that this holds. Okay, so I take my t of f, there it is up on the board. I take the norm of that, I bring it inside. Okay, using the triangle inequality, I get the sum of the absolute values of the an times the Fourier algebra norms of e to the 2 pi I n times these. And if these are uniformly bounded, then of course I get this continuity result of boundedness. And vice versa. Suppose that this was true. And then I simply have to test this on my function f, which is just a cosine sine at a frequency, single frequency. And then so this is simple, if and only if. So it really reduces down to this very concrete problem here. Okay, so let me now define. Let's define. Okay, let me define for each n. I'm going to define this function, which is e to the 2 pi I n times psi of t. I know that psi has this periodic part plus this linear part. And so let me look at its Fourier coefficients, which is what this is all about. I have to look at the Fourier coefficients at frequency k, and I need to sum them up. That's what this says for you to do. And so what is this? So this is I'm integrating over the circle. I'm integrating e to the 2 pi I. I have my function e to the psi of t, but then I have to integrate this against e to the minus 2 pi I kt. I'll put this all in one phase. dt. Okay. Oh, that's an oscillatory. Okay, so this is what I like. Okay. So let me call this phase function phi of t. And now you see the problem is we're trying to understand. I'm trying to, for fixed n, I have to understand this for all k and sum them up in absolute values. Okay, so I'm interested to remember, I'm trying to, let me try to, at the bottom of the board here, I'm trying to look at this guy, which is the sum of these coefficients. If I sum over all k. Okay, so I gotta look at all these oscillatory integrals. I gotta understand this for a fixed n. I gotta understand this as a function of k and sum them all up and then understand that, whether it's uniformly bounded in little n or not. So it's quite the task. Okay. But let's suppose here that let's suppose that the periodic part is not constant. There's some curvature. So let's suppose that's what people did. Let's suppose that the second derivative never vanishes. More generally, this analysis works if I assume that the second derivative never vanishes on some interval. Okay, if that's the case, then I have that this, notice that the second derivative of the phase, the linear part goes away, I get n times the second derivative of psi, and so I get a lower bound and an upper bound, like n. So in particular, I have by van der Korf's lemma, or by stationary phase, and so this is, you might hope, stationary phase. So van der Korf's lemma says I'm always going to have a bound from above by 1 over square root of n. And by stationary phase, you might hope that maybe this behaves like 1 over square root of n. Now that's only going to be the case if I really have a critical point. So I should have this was bad of me, should have looked more closely at my notes. The first thing you always do when you study the oscillatory intervals, you look at the first derivative, not the second derivative. I want to understand, right, the first derivative. So I really should have been looking first of all at the first derivative. And we see here the first derivative is n times the derivative side minus k. Okay, so that has no critical points. K is much bigger than n. So this never vanishes if k is much bigger than n. Okay, so that's the first thing. So if k is large compared to n, then I'm going to get a lot of decay by integrated by parts. Okay, so there's no place where the phase becomes stationary. So that tells me that in order to understand the sum in k, this is the Fourier algebra norm of this Fn, which is equal to 2 pi I of n times psi, that really I am really reduced to looking at those k's that are less than n. Okay, so that's the first step I forgot. Okay. Now I want to start to look at where k is less than n. These are the places where you have a critical point, where the phases become stationary. Then we look at the second derivative, always, and I'm supposing the second derivative vanishes. So this is now we turn to this guy here. And we see here that in this range, that we really are getting something that behaves like square root of n. And so indeed, in this thing here, we are getting, under this assumption, this seems to behave. This is not a rigorous argument, but I'm trying to convince you that I'm getting 1 over square root of n for these places where I have a critical point, so there are n of them. So I'm getting something that should behave like square root of n. And this was done rigorously, okay, under certain regularity conditions. So this was, for instance, carried out by Levinson. This is true under this assumption, okay? This was carried out by Levinson and also by Kahan. Okay, so Levinson always assumed a lot of regularity, and then he proves this bound, and therefore, and then Kahan removed the regularity. So of course, if this is behaving like square root of n, when I take the sup in n, it's not going to be true. So this tells me when there is curvature, when there is a nonlinear part, when the nonlinear part is not linear, the periodic part is not linear, then in fact this is telling me it looks like this is not going to happen. Okay, so this actually leads us to a famous result. Most people call this the Berlin-Helson theorem, but I think it should be called, and Walter Rudin agrees with me, well, in fact, I'm agreeing with Walter Rudin here, that this is really the result of Leibniz and Gahan. So again, this is in a paper of Leibniz, okay, from 1953 or 54. He had some regularity assumptions, and Gahan removed all these regularity assumptions in 56. Okay. But he shows, for instance, that if, so I have here a mapping to the circle, I have a mapping of the circle, and if the theorem is if I preserve, if this is an absolutely convergent Fourier series whenever F has an absolute convergent Fourier series, then this mapping has to be trivial. Then phi of e to the 2 pi I of t has to be e to the 2 pi I of some real number plus an integer times t. So the nonlinear part is constant, the periodic part is constant. Okay, so this is for some real number c and some integer L. Okay, so of course, if this is the mapping, it's very easy to see that the space of absolute convergent Fourier is preserved. But if it preserves the space, it has to be this affine map. Very simple. Okay, nice result. Okay, uses some hard analysis because we have to study these oscillatory intervals. Okay, now I want to now spend the rest of the time and this lecture is to start to back up a little bit. Okay. Want to start to develop a more general perspective on this problem. Okay. So I want to show how it relates. So I'm going to go back to this general problem of looking at homomorphisms between algebra homomorphisms. So not only linear maps between these finite spaces, but also that it's multiplicative. So if I take a convolution of two L1 functions and look at psi of that convolution, I get the convolution of psi of the individual ones. Okay. So we want to understand when if I had again two group algebras that are isomorphic, when is it the case that the underlying groups are isomorphic? Okay, so that's a hard problem. Sometimes the answer is yes, sometimes the answer is no. This is equivalent by taking the Fourier transform, as we've seen. Go back to this more abstract, I'll call this psi hat. Looking at the algebra homomorphisms of the associated Fourier algebras on the dual side, the dual group. Okay, so again, this is and here, what do I mean by psi hat? So on a function here, which is the Fourier transform of an L1 function, I just look at psi of that and get an L1 function here and then take its Fourier transform. So that's the definition of psi hat. So these are equivalent problems. Understanding when I have these are isomorphic as algebras, the same thing as understanding when these guys are isomorphic algebras. Okay, we've already seen the example. We've already seen when these two groups is the circle group. We've already seen an example of a basic algebra homomorphism, and that is just by composition with a mapping of the circle. Okay. Now, just to get at the problem of trying to understand this difficult problem, in what sense do these group algebras determine the underlying group? One way to try to understand is what do these algebra homomorphisms look like? Can we characterize them? So that's a basic fundamental problem. And so we've already seen one example. And so I want to look at this problem and see what algebra homomorphisms necessarily have to look like. So we're going to go back here. I'm going to take my some basic facts about Banach algebra. So B is a Banach algebra. Okay, I'm going to start with the notion of a complex homomorphism. If first of all, this H is linear. And 2, H is multiplicative. The Bonic algorithm has a vector space structure. So it's linear in the sense vector spaces and it's multiplication. So if I take a product of these two, H of that product is just the product of the H's. So and this is the basic lemma because this is semi-simple. We see it automatically has to be continuous, but we can say more. So H here from L1 of a, now I want to apply this to the Bonic algebra of a locally compact immediate group. So now I take a non-zero. This is important that I'm dealing with a non-zero. Of course, I can consider the zero complex homomorphism. But if I take a non-zero complex homomorphism, then there exists an element in the dual. There exists an element in the dual group that characterizes it. Okay. So there exists such that H of F, which is the Fourier transform of F. Okay. So this, if I start the mapping from F, so if I fix an element in the dual group, and I take the mapping F going to the Fourier transform F and evaluate it, this is valuation at that point, this is clearly a complex homomorphism. Right? That's because when if I take the product of two elements here, and then take its Fourier transform on an element here, this is just the product of these two elements. So that is a complex homomorphism, and it's non-zero just by the uniqueness of the Fourier transform, uniqueness of Fourier series. Okay, this gives me and all non-zero complex homomorphisms arise in this way. That's what this lemma says. Okay, notice that this automatically tells me, this has to be continuous. But what is the actual value of this thing? Well, what is the Allen-Fitting norm? This is bounded by the Allen-Fitting norm of the Fourier transform. The Allen-Fitting norm of the Fourier transform, just bringing the absolute values, is controlled by the L1 norm of the function, trivially, and this is by definition. This gives me the complex. So this gives me this tells me it's a bounded linear map on L1. Okay, with norm at most 1. Right, okay. Now let's start. And let's start with a non-zero. With a non-zero. Okay, I want to give a non-zero complex homomorphism. And H, okay, on. Now I'm going back to this problem. I'm going back to this problem here, this board. So I'm going to start with let me take a non-zero complex, this goes backwards, on L1 of G2. Okay, so since it's a non-zero complex homomorphism, that of course means by our lemma, so that means that there exists an element in the dual group. So that this H is realized by H sub gamma. So this is, I call this, we'll give a name to this. So the complex homomorphisms that arise by taking a integral function, computing its Fourier transform, and evaluation at that point, I'll just call it H sub gamma. Okay, so all non-zero complex homomorphisms on this group algebra arise in this way. So let's start with one. And now I can compose it with this map. So, so this, of course, note that if I take the composition of this complex homomorphism with psi, this gives me a complex homomorphism on L1 of G1. Okay, so remember, psi is a mapping from L1 of G1 to L1 of G2. So if I have a linear function on L1 of G2, actually a homomorphism on L1 of G2, by composing with what gives me a complex homomorphism on L1 of G1. Okay, because psi itself is a homomorphism, algebra homomorphism. It preserves multiplication and the additive structure. So this composition does. Okay, now this could be zero. This is the issue. It cannot, it turns out, because on the circle group that we started with, G1 and G2 are the integers, and so these guys, the dual groups, is the circle group. This is a connected group. So this never happens, but it can in general, as we'll see examples in the next lecture, this can be zero. So I want to, so we need to, if, big if this guy, if this composition is a non-zero, okay, it's definitely a complex homomorphism, but now if it's non-zero complex homomorphism, by our lemma, then there exists an element which of course depends on this homomorphism, depends on this guy, depends on this element in G2. Where is it? This gives me an element in the dual group of G1, such that I have here this guy at psi hat of F hats. It's just composition with such that I'll write this in short notation, such that I have this guy H opposed to psi. It's just H, so alpha gamma. And that's a composition. That's looking like, when I look at this side, that is just looking like a composition on the Fourier transform side with a mapping between the dual groups. But it's a mapping of a subset of the dual group. And so I'll finish here by, I'll just take buttons. So I'm starting with the general homomorphism. I'm starting with the general homomorphism between these group algebras, between two L1 of G1 and L1 of G2. And what do we get? Hence, there exists a mapping from Y into G2 hat. Okay, so Y is a G1. Such that on the Fourier transform side, at gamma, this is just composition. The Fourier transform with this mapping gamma. So, or if you like more, this is bringing into play this subset Y. I have that on the Fourier transform side, I get that this is just composition. Okay, if gamma belongs to Y. And 0 if gamma does not belong to Y. So we started with a general. We started with a general mapping homomorphism from L1 of G1 into L1 of G2. We found a subset. So Y here is a subset of the dual group of G2. It's precisely sorry. Okay, so this is, sorry, I should have defined Y. What Y is. Y is precisely those elements. Sorry. Sorry. Y, by definition, is precisely those elements in the dual group of G2, such that this mapping, such that H sub gamma composed with psi is non-zero. Okay, so this composition, because psi is a algebra homomorphism, composition with an algebra homomorphism is an algebra homomorphism. This is a complex homomorphism, okay, always, but it may be zero. So I just look at those elements such that this composition is non-zero. So that actually gives me then a mapping from that element, from those subsets so that this composition is this composition, only for those. And then everything else, by definition of not being in here, I actually have that this composition is 0. Okay. So to characterize, so now the job here is that we need to, so we have here, so for all elements, any algebra homomorphism, really we have a pretty good description. Gives rise to a subset, and a mapping from this subset of dual elements into G1. So think of this as the circle to the circle. So that on the Fourier transform side, this algebra homomorphism is just composition with this. There's a change in variables. So I'll finish here. What we're going to start next time is to start to think. So this becomes, it's a little bit more complicated problem. Not all homomorphisms is just going to be given by composition from a mapping between dual spaces. There's also this added thing. We have this extra subset Y. So in order to characterize these guys, we're going to have to find all of those subsets of the dual group of G2 and mappings from that subset into the dual group of G1, so that this guy transports L1 of G1 into L1 of G2. So we reduce in order to try to find all of those. So not every subset, not every mapping from a subset is going to give rise to a homomorphism. But to find those homomorphisms, we just have to find these two guys. Okay, so we'll start the discussion tomorrow. This one.
Thank you again. Any questions?
Very confusing enough.
I have maybe some simple, but
Yeah.
can you advance some examples which beyond the tools? Can you give some examples beyond the tools for this?
Beyond the torus.
Yeah.
Yeah, where this Y is not the whole thing, okay?
Yeah.
Yeah, so I don't know, discuss, but let me take the opportunity to answer that question here. Yeah, so I'm going to flip now. So here we've been talking about the previous one, the G1 is equal to G2 integers, and the dual spaces, therefore the circle group. And so we were looking at the Fourier algebra on the circle group. This is the space of absolute convergent Fourier series. Okay, and we saw that homomorphisms between little L1 to itself is characterized by trying to figure out which mappings of the circle preserve the space of absolute convergent Fourier series. So what's an example? It's not that. Let's flip the roles. Let's look at G1 equals G2 equals the torus. And now in dual groups, is equal to the integers. This is disconnected. Okay. So now we have to think a little bit. What does it mean? What does it mean? What is this guy here? These are functions of the map. These are what is an element to be in here? That's a sequence. So that comes from the Fourier transform we've gotten here. So that means that this sequence are the Fourier coefficients of some L1 function of the circle. Take an integral function of the circle, I can use Fourier coefficient. That gives me a sequence that goes to 0. Not a general sequence, but those are the sequences that are here. Okay. Now let me give you an example, and this is here we are. So let me now take Y. Let me take Y to be not, so remember now, I'm going to get a subset. I'm going to look at a subgroup. So let me look at all multiples of some positive integer Q. Okay. And so now we take a mapping. Let me take a mapping from the subgroup into the integers. And I'm just going to define it to be the identity. We make it as simple as possible. Okay, so what we're asking for, so here's going to be my Fourier, here's going to be my algebra homomorphism between A of Z to A of Z. So I'm going to take now my function f, which is L1 of the circle, and look at its Fourier transform. These are the Fourier coefficients now. Okay, so that's going to give me a bunch of Fourier coefficients, and I'm just going to define this now to be just Fn, just the Fourier coefficient of f, whenever n is a multiple. And I'm going to define 0 if n is not a multiple. That defines. Now wait a minute. Okay, so that easily defines a algebra homomorphisms from A of Z into itself. Now, it's not clear if it preserves, if this actually, so in other words, is this guy? So I start with an integral function. So is this guy coming from the Fourier coefficients of some integral function? That's not clear. So is it possible to construct an integral function whose Fourier coefficients vanish when supported along this subgroup and vanishes otherwise? The answer is yes. Okay, so here is, I'm going to take as my g. Okay, this is so my g of x. So start with g of x. Okay, and then which I'm going to define to be f of q times x. Remember, f is periodic at period 1, but I'm only going to do this for x's between -1 over 2q and 1 over half q. So I'm taking a very small part minus a half to a half. So if q times x is between minus a half and half. So that's in the unit integral. So f is 1 periodic. Okay, so f is this. So I have my f, which is an integral function. And I define it as 0 otherwise. Okay. And now I look at this function. I'll call it g. What's it? How do I do math? I do g tilde. Okay, so this is. I'm going to take this guy, and I'm going to sum g of x plus L of q over all the integers. That's 1 periodic. That's integral. And now you compute the Fourier coefficients of this guy. So if the Fourier coefficient at n is a multiple of q, you get exactly the Fourier coefficient of f at that point. If it's not a multiple of q, the Fourier coefficients vanish. So this is why we need, so when we move away, and this is the observation of ultimate, and we were going to start here in the next lecture, okay? So if I want to start to think about this problem from other groups, not just trying to understand the algebra homomorphisms of the Fourier algebra of the circle, but now I'm interested in the algebra homomorphisms of the integers, the opposites, things become a little more complicated. Okay, I have to think about mappings now that are not necessarily from the dual group to the dual group. It has to be from certain subsets. Those subsets have to have structure. They have to belong to what's called the coset ring of this dual group. Okay. Look, don't worry, we'll start there tomorrow. So we have to start to think. So now the problem becomes, now remind you, don't worry, the problem becomes trying to understand what are the subsets. What are the subsets of the dual group of G2 and the mappings from that subset into so that when I take this composition, I actually get something that preserves, that maps it into. I have to understand what are those mappings. And I characterize, so I got to characterize not just the mappings from the circle to the circle, now I got to characterize not just mappings from the integers to the integers, but subsets of the integers that have some structure or the coset rings into the integers that have this property. Yeah, the problems were nice in the 1950s. Okay. So yes, yes, you could.
Yes, is there any sense to consider this situation where, for example, G1 is false and G2 is R, or vice versa?
Yes, of course.
Or one is totally disconnected.
What?
G1 is for instance Z and G2 is R.
Yeah.
One is totally disconnected and.
Okay, so which one do you want? Okay,
So
so,
no, this is up to you.
so the complicate, yes, we can consider any G1, G2, and we're gonna consider any G1, G2. Okay. The complications arise when the dual group of G2, the target, is disconnected. So we started with the problem on the integers, but it's really, you can talk about characterizing the Fourier algebras of the integral functions on this guy, but that's equivalent by the Fourier transform of understanding the homomorphisms of the Fourier algebras. The Fourier algebra is connected. So this problem is actually just about understanding the mappings of the circle to the circle, no subsets Y, mappings of the circle to the circle that preserve the space of absolutely convergent Fourier series, okay? That preserve the space. That's all, and we have this wonderful answer from Leibniz and Kahan, that only the linear, the affine maps do that job, none others. Now we have to ask, what are this, now when things become disconnected, I have to not only understand what are the mappings from Z to Z that preserve, that when I look at this mapping that preserve the Fourier algebra, the integers, get back to the Fourier algebra, the integers, it's mapping. But I also have to take into account certain subsets. What are the subsets of the integers and the mappings from that subset of the integers that actually preserve this space? Okay. So it's a little bit more complicated than that. But I just want to, I'm not going to go into this. This is not really my intention, but I just want to give you an appreciation of the complication. Okay. So, and the role that Walter Rudin played, and then the final resolution of this whole problem. But that's not going to be our main interest, because we're going to be interested in oscillatory angles, of course. What else is there? Okay, so I'll get back to that in the next lecture.
Thank you. So, maybe Ravi, we can just thank you at the end of the last lecture. This is,
Yeah, or you know,
yeah.
or in 3 weeks' time, I didn't have So when will my last lecture be? I don't know, November.